Hello and welcome back to Functional Analysis, and many thanks to all the people that support this channel on Steady or PayPal. We've already reached part 9 and we will talk about examples of Hilbert spaces today. Please recall that a Hilbert space is a real or complex vector space with an inner product such that the associated metric space is complete. Of course, most of you already know a typical example, namely Rn or Cn with the standard inner product. And this one is given by the sum, where you multiply the components. And the important thing in Cn would be that you have the complex conjugate in the first component. The next example is a generalization for an infinite dimension. It's the L2 space we already had in part 7 of this series. And there you might already guess what the inner product should be. It should be like this one, but you go to infinity there. Later in this video, I want to discuss with you why this is indeed an inner product for the vector space L2. However, first let me show you another infinite dimensional example. It's about continuous functions defined on the unit interval. Therefore I write 0, 1 for the domain and f for the codomain. Now you should know all these continuous functions together form an f-vector space with respect to the natural addition and scalar multiplication. And now for two functions f and g, we can define an inner product. Simply by looking at the integral from 0 to 1, where we put in the function f and the function g. And of course, in the complex case, we need the complex conjugation for the first function. Okay, I would say these three are one of the most important examples at the beginning of such a course. The first one gets us the normal, the Euclidean geometry in Rn or Cn. Part B then generalizes that to an infinite dimension, and part C gives us a geometry for continuous functions. However, in spite of having an inner product here on the right, we don't get out a Hilbert space in C. So please keep that in mind. We have an inner product, but the completeness fails here. Okay, we can talk about this later. First, I want to show you in part B that we have a Hilbert space. There you already know the completeness, so let's discuss the inner product part here. This means that we have to check all the properties. And the first thing should always be showing that this one is a well-defined map from L2 times L2 to F. This means that this limit as a series should always exist. However, for this we need some technical details I just want to do later in the series. So don't worry, there will be a video about that. Here we focus on the three properties of an inner product. And the first part is showing that it is positive definite. Which means when putting in the same vector x, we want to get out a non-negative number. Which is easy to see because we have xi times xi, and the first one is the complex conjugate 1 in the complex case. So in other words, it's the absolute value squared, which is clearly non-negative. And the other part would be looking at the case when the outcome is 0, which means by the calculation above, all the xi squared have to be 0. Which then of course means all the xi have to be 0. And in conclusion, this is of course the 0 vector itself. And now we know it's positive definite. Now going to the second property, which was that the inner product is conjugate symmetric. Of course, this is now very simple to show. Just look at the inner product yx, where we look at the complex conjugation. So let's mark that in green, and we have it then over the whole series. But of course, we can pull that inside. And then the normal calculation rules tell us that we have yi, xi complex conjugation. Which is then of course xy in this order. And now the last part, the third part, is the linearity in the second argument. So maybe that's already easy to see, but still, let's write it down. Since I don't want to get conflicts with the indices here, I use y and z as the two vectors in the second component. Now by definition, this is the inner product and we can write it as two series. And as you can see, this is simply the inner product with x and y and x and z. And now we can do the same for the homogeneous part, so we look at the inner product x lambda y, which is the series xi bar lambda yi. And there we can simply pull out the lambda factor, which is then lambda times the inner product. And indeed, that's the linearity. Now what we have learned here is that checking all three properties is often not hard at all. Here it was just a matter of writing it down. However, showing that the map itself is well defined could be a much harder problem. Hence, in this case, we will do that in another long video. Nevertheless, combining this with the three properties and the fact that this corresponding norm we find here makes L2 to a Banach space tells us that the whole thing is a Hilbert space. Don't forget, the completeness we've already discussed in part 7. In the upcoming video we don't talk about the technical details yet, but I want to show you all the nice properties a general inner product has. Okay, I hope I see you there, and I can also tell you that I put a link to a PDF version of this video in the description. And indeed, I want to do this for all upcoming videos. So please enjoy it, use it when you need it. And with this, thanks for listening and see you in the next video. Bye!